Hi, everyone. Hope everyone can hear all right. My name is...
Yes, ma'am, we can.
Good. Thank you for the feedback. My name is Giulia Cavallari. I'm a structural engineer at Arup, but I literally just joined last month. Therefore, the project that you see on the flyer of Amity University is a project of my time with Edge Consulting Engineers. And hello, team, if you're listening. And this project was done in collaboration with SFMGC Bahrain. And the reason why I'm here is because your lecturer, Vidya, has invited me for this guest lecture. And I met her through a community of engineers called Engineers Without Borders, the UAE chapter. If you want to know more about it, we can talk about it at the end. But now let's get started with the topic. The project I'm going to present is Perlin Path Visitor Center and Experience located in Muharraq, Bahrain. And we are going to look at the design and construction challenges and solutions for this project. And we will focus on the late stages of design, as we were not involved in the early stages of concept design and schematic design. We were presented with a scheme from the previous consultant, and we followed it up with the detailed design and the construction phase. So in simple terms, our role for this project was to make it work and make it buildable. The site is located in the historical district of Muharraq in Bahrain, and it is part of Bahrain Perlin Trail that stretches for about 3.5 kilometers through the alleyways of Bahrain. You can see here on the Google Maps picture, and in red is the precise location. And it covers an area of about 6,700 meters square. And on site, there are ancient ruins. The site is a UNESCO World Heritage Site listed in 2012. And the ruins date back about 300 years. And this project has been shaped around the ruins to preserve their integrity, and it symbolizes the embrace of cultural heritage. So the obvious thing that we have to do was to preserve the ruins and to add value to the site. The building shown in this render, the render is done by architect Valerio Olgiati, is an open space in fairface concrete and has strong geometric shapes. And each element that you see, floor, columns, walls, and roof, serve a structural function, and the architectural finishes are reduced to the very minimum. We are going to look at the structural system of this building, and the structure is standing on a foundation of a micropile draft, and the superstructure consists of wind towers. You see in pink. Wind towers are an element of a traditional element of the Middle Eastern architecture, and here have been replicated in a modern keep. And they were part of the lateral load resisting system together with the RC core, while the gravity loads were taken down from the roof to the foundation with RC columns that we see in red. The design process for this project started by building an ETABS model. And with the ETABS model, we have designed the wind towers and the cores. And we have passed the base reactions for the building to the geotechnical engineer, together with the load on the raft. The geotechnical engineers have modeled the foundation, and they have come up with a piling layout and have given us a set of spring stiffness for the micropiles. And we have used this information to model, to do a structural model of the foundation. and evaluate what is the vertical displacement for the foundation. We have repeated this process in an iterative way until the results from the geotechnical team and the results from the structural team reached convergence. And with this final layout for the piles, we have proceeded with the design of the post-tension raft. And once the site was available, we have done tests on the site by installing the test pile. And with the information from the test pile, we have revised again the design and gone through a few more iterations. And once satisfied with the convergence of the design from the geotechnical team and the structural team, we have proceeded with the construction. We are going to look in more detail at the foundation. So first of all, why have we chosen to use micropiles? Why not use a shallow foundation like pad footings or a raft? It's because the top soil strata was weak, and it was not suitable to spread the loads evenly, and we may incur into differential settlement. And this is not desirable. It could cause cracks in the building or failure in extreme cases. Therefore, we have decided to introduce micropiles to minimize the differential settlement and take the loads down to a deeper soil strata with a higher stiffness. So this is the idea behind the selection of a composite foundation made of micropiles and raft. So after we have built the structural model, we have passed the base reactions to the geotechnical engineers team, and they have used the information to produce a piling layout. With the piling layout, they have created the geotechnical model, and they have come up with two sets of stiffness for the piles. One is an upper bound pile springs. That is the case where the piles behave in a more stiff way and give more support to the structure, while the other scenario is the lower bound pile spring stiffness, where the foundation behaves more like a raft and therefore in a softer way. We see here on the left the output from the geotechnical model, and on the right the output from the structural model. And what is plotted here is the vertical displacement of the foundation. And we have values that range from 0 millimeters to 13 millimeters. And we see that the values are not the same from left to right, but they have a similar pattern. For example, you see this small C shape here, and therefore we were satisfied with the behavior of the foundation, and we could proceed with this piling layout, and we could proceed with the final design of the raft. It wasn't final because we had to revise again our assumption after the test pile installation and the test pile results. The test pile has been installed in May 2018, and you see a picture there from the site. So it's a steel case of 250 millimeter in diameter. It has a bearing plate on top, and it's grouted with 30 MPa grout. The first test pile that we have done actually had to be abandoned because cavities were found in the soil, so the results could not be considered reliable, and they had to, and the cavities had to be injected with grout. So we had to move the test pile to a different location and redo the test again. The test showed that the pile could have an ultimate load of about 1,000 kilonewton, and we were satisfied with this result because it was in line with our original design assumptions. Therefore, with minimum adjustments, we have revised the initial design, gone through a few more iterations from the process that I showed you a few slides back. And finally, we could proceed with the actual design of the raft. The site is quite large, is under 60 meters long and 45 meter wide. It only has one access on the left side from the main road, and is surrounded by existing buildings on the lower side, on the upper side, and in this corner there are existing buildings that could not be disturbed. Therefore, we had to work closely with the construction to ensure the logistics were planned carefully. We had to ensure that there was a continuous workflow outside, that delivery and storage of materials was constant and safe. And we had obviously to preserve the ancient ruins. You may see, if I zoom in, these crosses on boxes, and this is the location of the ruins. So there are quite a lot across the site. These are all the ruins that had to be preserved. So we had to work around these challenges and come up with a construction sequence that was satisfactory for the contractor. And this construction sequence has been changed throughout the construction phase a countless number of times. And every time the contractor had to change the sequence, the engineering team had to work with them to adapt the design. So the site has been subdivided into 9 pores, and to suit the shape of the construction sequence. And there are 6 movement joints, 1, 2, 3, 4, 5, 6. We can see in red, and there are 2 construction joints in blue that are used to split the large size of the pore and to keep this last pore free, because we needed the access from the road. So the construction sequence went like this. I hope this was the final one, because it has changed many times. And the movement joints were necessary to prevent cracking from restraints and control concentration of stresses where we had peculiar shapes, like, for example, at this location and this location. If we cast these 2 pores in one go, we could have caused a concentration of stresses and a lot of cracks at this location. So this is the raft foundation, and we are going to look at the design of the post-tensioning. Just a recap of what is post-tensioning. So post-tensioning is used to induce precompression on a concrete, and concrete, as we know, works well in compression and doesn't work so well in tension. Therefore, it's ideal to put compression on the concrete. And the sequence for post-tensioning is first the slab. The concrete slab is cast together with some conventional reinforcement, and the tendons that you see in black are inside a plastic duct, the white one that is empty at the beginning, and they are held in position by a dead end and a live end. You can zoom in to see how a dead end looks. It's just a system of reinforcement, of spiral reinforcement. Once the concrete is cast, this will hold in position the cables. And the live end on the other side is a special system that splits the strands in each tendon so that they can be pulled. Then a jack is inserted and the cables are pulled with a force. Once the cable are pulled, grout is injected in the duct, and the duct is completely filled with the grout, which is a material that is more fluid than concrete, so it's filling the duct completely. And then the tendons are cut, and finally the tendons that were in tension try to shorten and put the slab into compression. So we have applied this system to the design of our foundation, and the post-tension raft has been designed with flat cables with a uniform precompression, mainly for crack control and to minimize the reinforcement mesh. The tendons have been laid flat to cater for both upper and lower bound cases. We talked about the upper bound and lower bound cases for the pile stiffness. So the additional reinforcement that we have provided in this foundation was designed to cater for the two scenarios. One scenario where the piles behave in a more stiff way, and one scenario where the piles behave in a softer way. The top reinforcement has been designed for the scenario in which the piles are stiffer and they behave more like supports, while the bottom reinforcement has been designed for the opposite scenario when the piles are softer and we expect the foundation to behave more like a raft. Once we have finalized the post-tensioning design of the raft, it was time to start construction, and Micropiles installation started in June 2018. At that point, we were only 6 months away from the inauguration of the building that had been fixed for November and could not be postponed. And it was a very challenging site due to the archaeological constraints and the fragile ruins that had to be preserved. The ground vibration had to be kept to a minimum, preventing us from doing any major compaction. And there was only one site access, as we have seen before. So the piling machine had to drive all the way from the main road to the back of the site through the ruins, and that was very challenging. As you see, it can barely fit between the ruins. 172 micropiles were installed in just over 40 days, and including the preparation of pile head, which is the installation of the steel plate caps that are to be cast inside the raft. And this is the machine that we have seen in the previous picture. It's not small at all. And this is a view of the pour one. That was the first to complete the installation of the micropiles. And this is a view always of the pour one. Here you can see the pile heads with the steel plate already installed, and they started the reinforcement. This is the bottom reinforcement, and went very quickly on and was cast shortly after. This is another area, I believe is the pour 6 or 5. And you see the reinforcement and the cables going near the ruins and through, but all the ruins were boxed out. Therefore, we had to provide special edge details for the slab at all locations. These starter bars that we see here are the starter bars for the wind towers that were installed after the raft was cast. This is another close-up for the reinforcement and the cables going through the ruins in the raft foundation. And this is a picture showing after the casting of concrete. Special attention had to be paid to the curing of the concrete to prevent early cracking and to achieve a smooth surface and uniform pigmentation, because there were not going to be any finishes on top of the slab. The architect was very specific on the type of concrete that they wanted. It had to have golden pigments and a pinkish color that we can see in the pictures at the end. And obviously we had to prevent any cracking. So the concrete was cast during the night. It was August, it was very hot. In Bahrain, it's the same temperature as here in Dubai. So in the night, you can get the lowest temperature. But even so, the curing of the concrete had to be monitored 24 hours 7 to achieve a high level of quality. So this is enough for the foundation. We are going to move up into the superstructure. I'm going to look first at the wind towers, then the core, roof slab, and columns. So the wind towers are part of the lateral load resisting system. They are 10 meters tall, and in plan they are 1.5 meters by 1.5 up to 2 meters by 2 meters. If you see the size of one of my colleagues here, 10 meters are pretty tall. And they had a transfer system at 2 meter high, and they had another transfer system at the top. In each corner of the wind towers, there are 4 vertical pre-stressed bars of 32 millimeters diameters that are used to compensate the tension induced by the horizontal loads. So you can see in this picture, this is the duct that has a pre-stressed bar inside, and the system is similar to what we have seen before for the posttensioning. So the concrete will be cast, and then the bar is going to be stressed. The core wall was another challenge. If you look at this picture, the gray walls are just normal straight walls that go from the foundation to the roof, and they are vertical and they support the roof slab. But the red wall is inclined with a big angle, with a big elbow at mid-height, and this is 10 meters high as the columns. And to avoid the roof slab putting too much load into this inclined wall and creating a big moment at the base, we have decided to detach the roof slab from the wall. So we have introduced a movement joint. There is a gap between the roof and the wall. The roof slab is supported by these big beams. We see them in blue. They are a system and they take the load to the nearest walls. The wall has been modeled, and it seems complicated, but in reality it behaves in a very simple way. In the horizontal direction, it behaves like a fixed slab. So we see negative moment here, and positive in the midspan. And in the vertical direction, it behaves like a cantilever. Therefore, the moment is concentrated at the base of the wall. We see in blue where is the tension localized. So we knew precisely what type of reinforcement we had to provide. And from the picture before, most of the reinforcement is concentrated at this location, where the moment is highest, at the elbow joint, and at the connections with the side walls. This is a picture from site during construction. What I didn't mention yet is that this wall is 21 meters long. And I did mention it's 10-meter high, so it's 21-meter long without intermediate supports. And we had to work with the contractor to come up with a supporting system for the formwork and to ensure that this was not going to fall apart during construction, because the wall will behave as we have seen in this slide only in its final condition. The next challenge for this project was the connection of slab to columns. The architect wanted to achieve an apex at the top of the column to create a floating effect for the slab. And this was an architectural feature that we could not compromise. So we had to come up with a system to create something special, a special steel connection to insert into the concrete column to create this floating effect. And as you see, it's quite a chunky piece of steel. It's 30 to 50 millimeter thick. But you need to imagine that these columns are 10-meter high and they are 850 by 850 in cross section, and they are carrying the roof. Although we don't have any high load on the roof, the roof span is 7.5 meters by 7.5 meters, so the self-weight is quite a large area. So we have detailed this steel connection to carry the loads. We have detailed the slab for punching shear, so the slab is not shearing off the connection. And we had to ensure that during construction, this connection was going to be installed correctly and without offsets, so that with minimal offsets, so that we didn't induce any additional moment into the columns. So from this picture, we see the taper at the columns give the roof slab a floating effect, and the orientation, you see here there is a different orientation for the column apex, is a compromise between architectural feature and structural function. So for example, at locations where we had long spans, we couldn't accommodate this direction of the apex, and we had to turn it around, going into discussions with the architect to see what is the to see how to achieve best the architectural intent. The last challenge for this project was the roof slab. It has large cantilevers, as you can see at this location. It's about 5 meters, and there are some large spans. For example, between these two columns is 15 meters, and there are a lot of voids that are architectural features. And for these reasons, we decided for a PT slab with upstand beams. And however, it's not a normal PT slab because of all the feature voids. We had to concentrate the cables at the column strips. Therefore, we came up with a banded PT system and RC slab in between the column strips. The roof was divided into 3 pours because of the large size. Is still under 60 meters long. We couldn't cast the roof slab in one go, so it had to be divided into 3 pours, introducing 1 construction joint approximately here and 1 movement joint approximately here. This had to be introduced after a thermal analysis showed the effects of temperature on a permanently exposed slab. So the temperature was inducing movement into the wind towers, and this was creating additional moments and problems for the design of the towers and the foundation. So the movement joint separated the slab and shortened the length of the slab. From these pictures, we can see clearly the large cantilevers here and the floating effect of the slab above the column apex, and the large feature voids. These feature voids have changed throughout the project about 100 times. Their orientation and their location has changed so many times. But in the end, we come up with some standard details that could be applied based on the size of the void and could be repeated to simplify the life of the contractor. So just to summarize, the roof slab system is a flat slab with upstand beams. The beams are 750 deep and 1.2 meter wide. The ear span is 7.5 meters to 15 meters internal, and some cantilevers are up to 5 meters. We have used a bounded PT system to suit the location of the voids. It's a very long slab, about 160 meters, and it had to be subdivided into a number of pores. And we have introduced one movement joint to reduce the excessive shrinkage and strains into the concrete. So in summary, we had a set of design challenges and we found design solutions. So the variable ground conditions were not suitable for a raft or for individual pad footings. Therefore, we have decided to use a micropile raft to control the differential movement and limit the settlement. The concrete had to be exposed with no finishes, and this was a very strict architectural requirement. So we used post-tensioning to control the cracking and to reduce the total amount of reinforcement into the raft foundation. The roof slab had to add a floating effect, and we came up with a special steel connection to create a column apex. And we had to achieve a thin roof slab with large cantilevers and large spans and incorporate a lot of feature voids. And to do so, we have used a banded two-ways PT system and with a suspended slab and upstand beams. So these were the design challenges, and then we had construction challenges. The construction challenges is that the large site only had one access, and we had to develop the construction sequence with the constructor and rearrange it several times to ensure progress at site, materials delivery, and continuity of work. Another construction challenge is that it's a UNESCO listed site with ancient ruins, and we had to keep vibration to a minimum and preserve the ruins without any damage. And another challenge was that the inclined wall was going to be self-supported only at the completion of the project. Therefore, we had to support it temporarily to ensure safety, and we had to add some extra piles to support the temporary condition. In summary, any project that you come across is a set of challenges, design and construction challenges. Sometimes they are very complex, and we as engineers need to find solutions that are safe, code compliant, cost effective to keep the clients happy, and they have to respect the architectural intent and vision, and they have to take into account the impact on the environment. And to move from challenges to solutions, obviously you have your engineering knowledge and your education, but you have to keep yourself continually educated. So there are forms to be constantly updated, like, for example, being part of an institution like the Institution of Civil Engineers or the Institution of Structural Engineers, of which I am a member, and if you have questions, we can talk about it later. And you will need to work as a team with your colleagues, and you will need to find engineering communities to help you progress. And they can be in your team, or they can be across the world. For example, for this project, our team was scattered everywhere. And with hello.
Joseph?
Yeah. Okay. And that is all from me today. Thank you. And let's see if you have any questions.
Thank you so much, Giulia. Now, I would request students to switch on their mic, and I'll give 10 to 15 minutes if it's possible for the discussion. Is that okay with you?
Yeah.
Yeah. And I believe we have today John joined us for the meeting. Hi, John.
Hello, everyone. Yeah, I'm here.
Yeah.
So
Hi,
can we
John.
have
Giulia.
Thank you so much. Thank you so much, John, for joining.
Oh, it's a pleasure. It was a great little lecture there by Giulia.
And now, students, you all can unmute your mic, and then whatever the question you can ask. John and Giulia both are structural experts, so whatever questions you have related to the structures and related to construction, please feel free to ask question. We have 10 to 15 minutes. And we also have our Dean of Engineering, Dr. Anand, who have joined our meeting. Good afternoon, sir.
Good afternoon, Vidya. Congratulations to all of you.
Thank you, sir. We have two of our guests, Prince and Giulia, with us today.
Hi, Prince, and hi, Giulia.
Hi.
Hi.
Good to meet you.
Any questions from the students?
Students, now you all may unmute your mic and you can start asking questions, those who have noted the doubts.
Or maybe I confused them too much.
Is it true? Did she confuse you so much?
Hi, Giulia. It's very pleasure taking the part of in this presentation. It's really useful. Like, we learned a lot of things. You didn't confuse us, of course. There was a lot of information, very interesting. So I wanted to hear about morely in terms of the piles that you have some voids in between. I'm not sure about the architectural purpose of it. Can you explain more about them? Like the one you're showing in the last slide, you see there are some voids in the columns.
Am I still sharing my screen?
Yeah,
yes, Giulia,
sharing
you're
your
still
screen,
sharing.
yes.
Okay. So you're referring. 1 second. Don't know what happened here. You're talking about these voids?
Yeah, those voids.
Okay,
Are they
so
really taking some loads? Those things?
okay, so this is a wind tower, and the purpose of this void is to let the air out. So if we go back a few slides, we can see the wind tower here. And the architectural intent, okay, obviously I'm not an architect, but I've been explained this by the team of Valerio. And the hot air comes in, travels down to the base, and comes out through that void that you've seen here, fresh.
So they actually don't take any loads, right?
These wind towers?
Yeah.
Yes, they take load. They take vertical loads and they take horizontal loads. So for how it works is there are continuous columns at the corner, and at the corners we have pre-stressed bars that help with the tension, because these wind towers also take the horizontal loads. So I draw here horizontal load coming in.
Okay. Nothing from the slab, right?
Yeah, they also take load from the slab at all corners.
Okay. Okay.
So at this, above this, there is a transfer system. It's a cross inside the wind towers. So this is the base, and
Okay. Now
above
I get it. Now I'm matching
this is
them.
the void
Now I
that
get it.
the void that you see in the last picture, and then this is above.
All right. Thank you.
Welcome.
Julia, we have few architecture students also along with us today. I wanted to ask if they have any doubts because we went more on the structural side. Anyone from architecture batch?
Good afternoon, ma'am. I'm Freda from the architecture batch, and your presentation was really helpful for us in the structural terms. We wanted to know what is the importance of a UNESCO site, Yeah, I believe one of your projects was under the UNESCO site, right?
Yes.
So, what is the importance of a UNESCO site? How important is it?
Okay. I've not been in touch with the conservation team, but what it means to have a UNESCO site means that whatever is at site before you start your construction has to be preserved. So the ancient ruins that you've seen at the beginning of the presentation, they could not be removed, relocated, or damaged and readjusted. They just had to be preserved like they were found. And having a UNESCO site, I think, brings prestige to Bahrain in terms of culture, and they can organize cultural events, have more visitors. This is the meaning of having a UNESCO site. At least to my understanding, but I do some research on that matter.
Thank you, ma'am. Thank you.
Any more questions?
Yeah. Hi, Julia. Deepak here. It was really, hi. It was really a nice presentation and impressive one. I want to ask one question from the construction management point of view that you have mentioned about the time constraint for the entire project duration of 6 months. Okay.
Yeah.
As an architect and as a construction manager, I'm curious to know that have you thought about the post-tension slab options while casting the roof slab? Because I'm sure that 6 pours, like it was a tedious task for any contractor as well as for any structural engineer. So have you thought about that option, or if not, like why you rejected that one?
Sorry, what is it that we rejected?
The post-tension slab option. Like, have you thought about the post-tension slab option?
Yeah, they are post-tensioned.
No. Sorry, I just want to say precast option.
No, that was not an option because we couldn't have joints. The architect was very specific. The concrete has to be cast in situ.
Okay, but is it possible, like maybe for any other project similar to this one? Okay, so the like precast can be a feasible option according to you?
Yeah, if you don't have any limitation in terms of architect specification, you could have chosen a different way. Even if this project could have been achieved with, the quality of the finishes could have been achieved with cladding, you could have considered a steel structure. Something entirely different could have been an option.
Okay. Thank you.
Any more questions? Students from CPM, do you have any more questions?
Okay.
I think students got really impressed with your presentation. Now they don't have any doubts. So I would request John, if you can talk a little bit about our Engineers Without Borders and our current engagement with this situation.
I
John,
think he
is
will
not
be.
there? Yeah, he was
Go on,
there.
sorry, you, Julia, go on.
I think he will be talking to you about iStructE if you are interested.
Ah, okay, yeah. Because the students, because mostly are very new to Engineers Without Borders either.
Okay, they can send me an email about that.
Sure.
You can pass them my email.
Yeah, sure, Julia.
Yep. But if anyone is interested in the Institution of Structural Engineers and how to become a member, we can answer that now.
Because mostly all the civil engineering students and architecture students are a part of Institution of Civil Engineers, which is ICE. They have not started. Yeah, we have not started a chapter for iStructE. We have just started last year for getting in touch with Mohammed, but then we haven't established it yet, which we'll be doing it this year.
Okay.
So what we would probably prefer you to do is we've set up a chapter, a young members chapter. However, we don't call it a chapter. We call it the Young Members Group. Now, this is being headed up and has had the official go-ahead by the Institute of Structural Engineers. And we currently have the chair for that Young Members Group is from Harriet Watt.
Young Members Group.
So if anyone wants to be a part of that, then I'm going to suggest you contact me or Giulia, and we can put you in contact with Ines from Harriet Watt. And they've started the Young Members chapter for the Institute of Structural Engineers. So I wanted to try and get a tie-in for all of the universities in and around where you are. So this is going to be the focal point. So there's already something set up. So anyone that wants to be a part of that, it's a very dynamic group. And as soon as we're over this current situation, it's going to be very vibrant. So just get in contact with me or Giulia.
Sure, John. Sure, I will do that. I think our Pro-Vice Chancellor also has joined the meeting. Good afternoon, sir. I think he's not available. Yeah. Thank you so much, Giulia. Thank you so much for your time. Thank you so much, John.
Thank you.
I'm there.
Yes, sir. Good afternoon, sir.
Yeah. I was talking from here. I thought you were not able to, it was not audible that side.
Yeah, yes, sir. I think your mic was on mute.
Okay. So nice. I wasn't able to follow the complete lecture, but I was able to follow the last few sessions. I particularly enjoyed our guests talking, Ms. Cavallari, as well as our guest, the other guests as well. In fact, I saw a few PowerPoints from both of you. Mr. Bampton as well. Thank you very much for joining. And it's a real pleasure for all of us, especially at a time when there is a very tough time everybody is undergoing, and still we are able to find some way of interacting with students. And when Ms. Vidya was telling us about your expertise and the in-depth work and the detail with which you have done on different things, definitely experts like you are very, very important and useful when it comes to understanding for students. This session will not stop here. Vidya, you will work out some way of remaining connected with our guests.
Sure, sir. I would do that.
And their expertise is very valuable. Years of experience is a lot of wisdom. And with this, we should be able to help our students, not only from Amity University, from other universities as well. We are also having a few seminar series in our home campus. It's hosted by different people, different experts, very senior people like you, professionals in their field, very, very senior CEOs, chairmen, and different people who are very, very important and useful, especially to advise students at this point in time. Thank you very much. Thanks for joining at this time at very short notices. And I'm sure all the students enjoyed.
Yeah, thank you.
Pleasure.
Thank you.
Thank you so much, sir. Thank you so much. Thank you so much, Julia. Thank you so much, John.
Bye.
Bye-bye.
Bye-bye, everyone.
Thank you. Bye bye.